Okay. So if you remember the last class, we were discussing about air fuel ratio, or what is the equivalence ratio, or what is the relative air fuel ratio, or lambda. All these things we have discussed, and then we also try to find it out the equivalence ratio or air fuel ratio for chemically correct air fuel mixture for some of the fuel. That's really very good. And we also consider the concept of what is the lean mixture, what is the rich mixture, what is the stoichiometric mixtures, because these are the some of the things is really very important when we are going to discuss something like combustion or so many things, because these are the terminology that we are going to use frequently. So the physical meaning of some this terminology has to be very clear. So once this is over to us, now what, before going to the realistic condition, okay, realistic conditions, it means what is the valve timing diagram, how the air fuel mixture takes place or forms in the real condition, how the combustion takes place, what is happening, what is the physics of the combustion is taking place, how the emissions forms. Before going all these things, what I would like to recap your some of the things that you have already studied in probably in the thermodynamics regarding the thermodynamic cycle, in which we are going to just recap the Otto cycle and diesel cycle. So I'm assuming that you have already gone through in the details in your thermodynamics. Here I'm just trying to touch it. So in thermodynamic cycles, as far as the Otto cycle and the diesel cycle is concerned, we are going to there are different cycles depending upon the what kind of the assumptions you are making it. The ideal cycle, air cycle, fuel air cycle, and the actual cycle. Now, when we are discussing about the ideal cycle, then we are making some assumption. So these are the some of the things that has to be very clear in your mind, or it has to be very clear to you that what are the assumptions you are taking in order to do some sort of calculation for ideal cycle. So the assumptions is working medium is a perfect gas. The specific heats are constant throughout the cycle. So it is not varying, even though it is a temperature dependent parameter, but we are assuming that it is a constant. The third assumption is heat is supplied to the system or rejected from the system. It is an instantaneous process. It is happening very fast, very fast. And the third one, we are assuming that there is a no heat loss. So these are the assumptions that on which we will consider about the ideal cycle. Working medium is a perfect gas. A specific heat constant is heats are constant. Heat supplied or rejected is taking place very fast, instantaneously, and there is no loss of the heat to the surrounding. So in that way, whatever the cycle represents, and then we calculate the performance of the cycle, it is representing the upper limit of that cycle. That is, theoretically, it may not be possible to obtain it. Then what is happening that we are going to simplify these assumptions and then try to go to the realistic condition. So in next slide, when we are coming to the air cycle, so here two of the assumptions is going to be slightly changed. The working medium is air. In ideal cycle, it was a perfect gas. Here the working medium is air. Specific heats are variable. So now this is the second assumption has completely is matching with the actual condition. But still all these three assumptions, it is still far away from the realistic condition. So in air cycle, we assume that working medium is a gas. Specific heats are now variable. It is varying. But heat supplied or rejected still is taking place instantaneously. And still we are assuming that there is a no heat loss. Then when we will come to the fuel air cycle, then this cycle is representing the closest approximation to the actual cycle. Because now the working medium here is we are considering as the actual working medium, where it is a mixture of fuel. Working medium is a mixture of fuel, air, and residual gas, or mixture of air and residual gas. So may I ask these questions to you that why I am writing here working medium is mixture of fuel, air, and residual gas. That is the one thing, or mixture of air and residual. So in the next step, I have removed the fuel, and it is only I'm considering it as a mixture of air and residual gas, or in a second case where I'm assuming that working medium is a mixture of fuel, air, and residual gas. Why I'm taking these two different kind of the mixture? In one case, we are considering as the working medium is the mixture of fuel, air, and residual gas. And in the second case, we are considering that the working medium is a mixture of mixture of air and residual gas only. So why it is happening like that? In which condition it is going to be true? Anyone?
In two cycle.
What is?
Post combustion.
Post combustion. In one of the case, we are considering it is a mixture of working medium is a mixture of fuel, air, and residual gas. And in the second case, we are considering it as only air and residual gas. Particularly think from the intake point of view, when the suction stroke. During the suction stroke, in which case, or for which
So
kind?
one is for gasoline and one is for diesel.
Yes, that is what I was expecting to get it. Okay. So in this cycle, fuel air cycle, the working medium is we are considering as the actual working medium. OK. After the combustion, working medium is a mixture of combustion product. So the working medium itself is also changing. Variable specific heat that is also represents for the actual cycle. But still these two assumptions it is still associated that heat is supplied or rejected instantaneously and there is no heat loss. So if you now consider from the ideal cycle to air cycle to fuel air cycle, it is the only we are playing with these two kind fuel air two assumptions, and we have simplified or we have taken to the actual condition in the fuel air cycle compared to the other cycles. But the last two assumptions where the heat is supplied or rejected instantaneously or there is no heat loss, it is still it is a ideal condition. So anyway, we are not going to consider all different cycles. And then there's actual cycles. Actual cycles when we are going to do the experiments, and then we are going to see that where mixture is fuel, air, residual gas after the combustion. It is a combustion product of the different kind of the species. Specific are variable where heat is supplied or rejected during during the finite time, and there is a heat loss is also taking place. So that is representing our actual cycle. So actual cycle, how the actual cycle looks like, and how much it is deviating from the ideal cycle, that it is also possible to study it. So let us start with the Otto cycle, that is the ideal cycle that you have already studied. That is what this picture is representing, the PV diagram of the Otto cycle. Okay, in which one, so on the y-axis we have a pressure, and the x-axis we have a volume. Okay, and the different states is representing by the points 1, 2, 3, 4, 5, 6, 6, 1. Then again it is going on 6, 1, 2, 3, 4, 5, 6. Now, see, the thing is what it is representing, the different lines. 1 to 2, it is representing a compression stroke in the ideal cycle, and it is a isentropic process. Then when the piston is reached, okay, let me before that, let me ask the questions. If the piston is at this point, okay, what we can say, is it at the bottom dead center or it is a top dead center?
Bottom right.
Bottom dead center. And once the piston is here, then it is a top dead center. Okay, so with this with this picture, what is the total volume of the engine?
V1.
V1, very good. Displacement volume?
V1 minus V2.
And clearance volume?
V2.
V2, very good. And then let me tell one more thing. What is the, how do we define the compression ratio here?
V1 by V2.
V1 by V2, very good, absolutely correct, very good. So one is representing when piston is at the bottom dead center, and the second or 3, it is representing the volume when piston is at the top dead center. So when from 1 to 2, the piston is moving from the bottom dead center to the top dead center, and it is a compression stroke. 1 to 2, it is a compression stroke, and it is considered as the isentropic process. When piston is at point 2, then heat is added here, and the combustion is taking place at the constant volume. Because of that, the pressure and temperature is increasing, and it is reaching at the V3. Then because of the high pressure and temperature, it is acting on the piston, and it is pushing down. So the piston is traveling, or piston is now coming back from the top dead center to the bottom dead center. That is the expansion stroke. 3 to 4, it is a expansion stroke, and it is still taking, it is a isentropic process. And then 4 to 1, it is a heat rejection process. Now, can anyone tell me what we are understanding the meaning of combustion is taking place at constant volume? What does it mean? Piston is taking place, combustion is taking place at constant volume. Or let me ask in another ways. Right now, you are seeing PV diagram of the Otto cycle, where y-axis is representing the pressure variation inside the combustion chamber and the x-axis is representing at the volume. But if I ask to you to plot the Otto cycle on the P theta diagram, it means on the y-axis it will be remain as the pressure and the x-axis represent the crank angle rotation of the crankshaft. Theta, that is the crank angle rotation. So that right now you are seeing it is a PV diagram and I'm asking you to draw it on the P theta diagram, where the x-axis, the volume has to be replaced with the crank angle. And then represent all the four stages. 1, 2, 3, 4, 1. Can you please do that? Think about that. How the PV diagram of the Otto cycle will be changed to the P theta diagram. Plot a line, that is horizontal line. Let us suppose it is a crank angle rotation. Vary the crank angle from minus 360 to 360. Minus 360 to minus 180. It will show you the intake stroke. Minus 180 to 0. It is a compression stroke. 0 to 180. It is a expansion stroke. 180 to 360. It will be the exhaust stroke. So minus 360 to 360. Take it as for the informity among the classes. I'm asking to draw first of all a horizontal line, mark it as minus 360 to 360 and 0 wherever it is coming 0. At 0 draw the vertical line and represent that is representing your y-axis in which you are taking as the pressure. And then think about that how the pressure will vary from minus 360 to minus 180, then minus 180 to 0, then 0 to 180, and then 180 to 360. Please do it and show it to me or discuss with me. I hope question is clear. We have a PV diagram of the Otto cycle. And the question is to redraw the Otto cycle on the P theta diagram. Okay. If question is not clear to you, then you may ask to why. I will explain once again. And any one of you, please come forward and tell me that what you think about it, how you are going to do that. Or if you have done it, can you switch on the video and show me to the graph? Mayur, are you there? Mayur? Manu Sehgal? Nobody is at the desk? May I ask why you are forcing me to ask to switch on the video of all of you? Okay, my mic is not working. Come on, man. How it is possible that your mic is not working? Manu, what is the case with you? Anyway. Hey, Rohit, can you explain me that what you are thinking about that? Okay, so some of you to whom I am calling and you are not responding, that is not a very good situation, okay? Not responding either in sense of the chat or in sense of the switch on the mic, it is not good at all. It's better to not join the class than the joining the class and not be at the desk. Okay, anyone would you like to put your views that how it can be converted to PV diagram to the P theta diagram on how it will look like? No ideas? Prince, go ahead.
Gives gives equation for that.
Which equation?
I mean, like delta G is equal to delta S H minus T delta H. Like,
don't go too far. Huh? This question is very simple. This question is very simple. That is what I'm giving the hint. We don't need to go in such details. Only think about that if this is the PV diagram and if I have to convert it, all of you know that volume and the crank angle rotation. How the volume of the engine is related with the rotation of the crankshaft. There is a geometrical correlation. It is very easy to establish it. Even that equation is not needed right now. We are just thinking, we have to think that if I have to redraw this graph on the P theta diagram, then how the pressure inside the combustion chamber is going to vary. Okay, I'm holding these questions right now. But think about that. But another thing is that what do you understand the physical meaning of the combustion is taking place at constant volume? That has to be clear. What do you understand the physical meaning? The combustion is taking place at constant volume. In terms of the engine, okay. What is coming in your mind? What thought is coming in your mind when this statement is, you are reading this statement that combustion is taking place at constant volume?
The piston is at the top dead center.
Piston is at the top dead center. Okay. Prince, do you want to say something?
volume will be constant, like
volume will be constant. Yes, constant volume is constant volume. Yes. What else?
Sir, it is for very short time.
Short time.
Yeah.
Yes, that is what the combustion is taking place very fast, because piston is not going to be stay at the top dead center. So if combustion has to be take place at the constant volume, then the process of the combustion itself has to be very fast. Very fast, and then it can be considered as the pressure combustion is taking place at constant volume. Otherwise, another way is not possible, that piston is going to the top dead center and it is going to be remains fixed. there until the combustion is not going to be finished. So in another sense that combustion is taking place so fast that it is not, it's so fast that it's finishing is delta T tends to the zero, something like that. And then that is the what the assumption is coming in our mind. In reality, obviously, it is not going to be happen. It takes place, combustion it takes place over the finite interval of the crank angle. So if that concept is very clear to you, that combustion is taking place at constant volume, it means it's constant volume. How the constant volume will be takes place when the theta crank angle theta is not changing during the 2 to 3 process, the theta is not changing. So that it means you are understanding the whole things. The only thing is that you have to take the pen and pencil and draw 2-3 graphs, and probably you will be in the positions to redraw this P diagram on the P theta diagram. So do it at your end. Okay. In the Auto cycle, what is our aim? Our aim in discussing this ideal cycle is to get some values to calculate some thermal efficiency, work output, IMEP or kind of the things that will give us the standard, or that will give us the references that this is the maximum value of the any performance parameter. And then when we will do some kind of the experiments, and then we can get this value of the same parameters, then we can compare it with the actual, with the ideal conditions, and then we judge ourselves that how far we are, and then how we can reach at that point, or how we can go closer to that point. So that is the what our aim to study this ideal cycle. So in which when you study the ideal cycle, there's one of the things is to calculate the thermal efficiency of this Otto cycle. So thermal efficiency, if I have to do calculate, so 2 to 3 it is a heat addition, and 4 to 1 it is a heat rejection procedure. A process is taking place. So the thermal efficiency, it is the output divided by input. So input is the heat supplied to the engine, and the output we can take it as the heat supplied minus the heat rejected. That is what we are going to get the total work done. So the thermal efficiency we can write down that heat supplied during the process of 2-3 minus heat rejection at the process of 4-1 divided by the heat supplied. Since both process 2 to 3 and 4-1 is taking place at constant volume, then we can write the heat supplied, that is MCV T3 minus T2, and the heat rejection we can write MCV T4 minus T1. And then we can put these values MCV T3 minus T2, that is the heat supplied, and MCV T4 minus T1 as the heat rejected in these equations, and then we can get the thermal efficiency in terms of the temperature. 1 minus T4 minus T1 divided by T3 minus T2. Now our the compression ratio that you have, one of your friend is already discussed, that the compression ratio V1 is representing the total volume, V2 is representing the compression clearance volume. So the compression ratio of these Otto cycles, we can say that V1 divided by V2, total volume divided by the compression ratio. That is what it is representing, the compression ratio. And the thermal efficiency, it is coming in terms of the temperature here. Now it is possible, since we know that 1 to 2 is the isentropic process, 2 to 3 is a constant volume process, 3 to 4 again it is an isentropic process, and 4 to 1 it is a isentropic process. So we can utilize this relation and use the expression that ratio, and then it might be possible to write the thermal efficiency in terms of other parameters also. So what we can do, take the advantage of 1 to 2, that process isentropic process, try to establish the relations between temperature and volume, and then similarly do the same kind of the practice at with the process of 3 to 4, and then finally we will come back that this ratio T4 minus T1 divided by T4 minus T1 divided by T3 minus T2, it is nothing but it is coming, that ratio is equivalent to the T1 divided by T2. And then again we will utilize the concept of the compression ratio, and then finally we can reorganize this equation in terms of the compression ratio only. It is possible that thermal efficiency of the Otto cycle is defined by the 1 minus 1 divided by R to the power gamma minus 1, where R is the compression ratio, gamma is the polytropic constant. I would suggest to all of you that even though you have done so many numericals and done in your thermodynamic course, but these steps that I have skipped a lot of steps, please do it once again at your home or in your room, so that it is possible to do some of the numericals also. You may expect some of the numericals on these topics also. So the thermal efficiency of the Otto cycle on which their gasoline engine works is defined as in terms of the compression ratio and the polytropic constant only. That is 1 minus 1 divided by R to the power gamma minus 1. So when we draw the curve, like here we have on the y-axis we have a thermal efficiency, and the x-axis we have a compression ratio. Okay, and then the graph has been plotted for the different value of the polytropic constant, where gamma is taking as 1.4 to the 1.25. Okay, for 3 different value of the gamma, and then thermal efficiency has been plotted against the compression ratio, and then see how it is varying. With increasing the compression ratio, the thermal efficiency of the Otto cycle is increasing. And for a given compression ratio, if we increase the polytropic constant, then the thermal efficiency is also going to be increased. That is what it is indicating from this equation. So that's really very good that thermal efficiency of the Otto cycle is increasing with the compression ratio. Then anyway, when we are designing our any device or mechanical device, energy conversion device, then what is our main motive? Our main motive is to somehow to improve the thermal efficiency of our device. And then here what we are getting it that ideally that if we increase the compression ratio, the thermal efficiency of the engine is going to be increased. So anyone can think that, okay, we will design the Otto cycle, or we can design the gasoline engine that has a maximum compression ratio. But if you remember one of the class or some of the class where we have discussed about the range of the compression ratio for the gasoline and the diesel engine, where we have discussed that the the compression ratio of the gasoline engine varies from around 6 to 12. That is the maximum what we are getting it here up to. And for the diesel engine, the compression ratio generally it varies from 16 to around 22 or 24, whatever you can say. So ideally, we are saying that where a thermal efficiency is increasing with the compression ratio, but practically I am saying that it is restricted maximum within this range. Then the question is obviously comes into the mind that why, particularly for the gasoline engine, why we are stopping and why we are limited to the to a maximum compression ratio. Why can't we go more than 12 13, 14, 15. So that part of the things we also need to consider. That practically what is the constraints with the gasoline engine, that we are limited to a small range or a small value of compression ratio compared to the diesel engine, whereas that kind of the constants is not putting on the diesel engine, and then we are having a much larger or value of the compression ratio. Okay, that's fine. That we will consider. We will discuss this case whenever we come to that point. But here, at least for the ideal cycle, we assume, or that is what we are getting here. So that's fine. So compression ratio is increasing with the, sorry, thermal efficiency is increasing with the compression ratio, and it will also increase with the increasing the polytropic constant. Okay, so that is one of the parameter, thermal efficiency of the gasoline engine or auto cycle. Then we need to consider that what is the total work output. Okay, how we can calculate the work output. So the area enclosed this in within this curve, that is 1, 2, 3, 4. That is what it is giving us the work output. So we need to find it out what is the area of this enclosed part, for which what we can do, we calculate the total area that is coming under the curve of 3 to 4, and then we can subtract the areas that is coming under the curve of 1 and 2, and that will give you the area inside this enclosed curve, and that is what it has been written, that is the adiabatic process, work done by the adiabatic process, that is well known to all of you. Then P3 minus P3 V3 minus P4 V4 divided by gamma minus 1, and then this area will come P2 V2 minus P1 P1 divided by gamma minus 1. And when you will utilize the concept of the isentropic, adiabatic, and the constant volume process, you will find it out that ratio of P3 to P3 divided by P2 and P4 divided by P1, it is going to become constant. That is the pressure ratio, that is the P3 divided by P2 is going, the ratio is going to be the same as the ratio of P4 divided by P1. That you can try utilize this all the isentropic properties and the constant volume properties, and you will find it out. And latest term, that ratio, it is coming RP, and then coming it as a pressure ratio. And then this put this value of RP and find it out the compression ratio. Then it is possible to restructure this equation in terms of RP, R, P1, P1. And then finally the work output, it is going to be defined like these equations when you are reorganizing all the parameters. P1 P1 divided by gamma minus 1, RP minus 1, RP is the pressure ratio, divided by R to the power gamma minus 1 in minus 1. So that is what it is giving you the work output, total work output. Then another parameter, that is what it is coming, is the indicated mean effective pressure, IMEP. Indicated mean effective pressure, IMEP. Let us suppose we have a two engine of a different engine, and then we have to compare this engine, that which one is the we need to buy it. But both engine has a different volume, displacement volume. Okay, and one is giving some power, another is giving another power, and anyway they have a different displacement volume. Then it's really very difficult to compare these two engines, that which one is the good engine, because it is both engine, there is no parameter constants. Suppose if they both has a same volume, and then it's very easy to compare it, because those in that conditions displacement volume or total volume is the constant, then those engines which produce the more power, we can say it is a very good engine compared to the else. So when we have to compare between the or among the engines, the what we need to have a parameter that will be the independent of the displacement volume of the engine. If that parameter, if we can find it out any sort of the parameter that is independent of the displacement volume, and then it is better to compare the different engines on the basis of that parameter, and then we can say that which engine is good or compared to the relatively good. Indicated mean effective pressure is the one of the parameter that is the independent of the displacement volume of the engine, and that can be used that parameter to compare the engine performance of different engines. So what is the indicated mean effective pressure? Mathematically, let us define it out. So see that this picture in the, as we have already discussed, that pressure inside the combustion chamber varies in all four strokes from minimum to the from atmospheric to the maximum pressure always. So to simplify it, and that area within this curve 1, 2, 3, 4, it is giving you us the uh, power output or work output. So and V1 and V2 is the your displacement, V2 minus V1 is the displacement volume. So what we are going to do here, we are going to construct a rectangle, okay, within the given displacement volume. So the length of this rectangle is fixed, that is the displacement volume. And then the height of the rectangle we have to adjust in such a way. The height of the rectangle we have to adjust in such a way that the area of the rectangle A, B, C, D should be the same as the area of our Otto cycle 1, 2, 3, 4. Okay, so what I'm saying that within this displacement volume, we have, if we construct one rectangle in such a way that the area of the rectangle is the same as the area of the curve 1, 2, 3, 4, then the height of the rectangle, that is what this BC or AD, it is representing the indicated mean effective pressure. And that is what we are considering, that is the constant pressure acting during the compression and the expansion process. So utilizing this concept, we are writing here that area of 1, 2, 3, 4 equal to the area of A, B, C, D. The area of 1, 2, 3, 4 yeah, area of 1, 2, 3, 4, it is nothing but it is the net work done by the cycle. And this area, if I have to write of the area of this rectangle, then what we can write, this indicated mean effective pressure, that is this length into AB. AB is nothing but V1 minus V2. So the indicated mean effective pressure is what? It is the net work done divided by the displacement volume. So indicated mean effective pressure is what? It is defined as the net work done divided by the displacement volume. Net work done we have already calculated here. Okay, if this equation is divided by the displacement volume, that is V1 minus V2, and then we are going to get it the indicated mean effective pressure. Okay. So do you have any question here up to? So what are the parameters we have calculated with the Otto cycles? It is the thermal efficiency, work done, indicated mean effective pressure. The similar kind of the things we need to do with diesel cycle. And then there is one cycle that is called dual cycle. It is a sandwich of the Otto and diesel cycle that we need to also consider in a very briefly manner. Then this we will try to wrap up this cycle in the next class also. Do you have any question here? Can anyone tell me then in Otto cycle which one is representing the intake stroke and the exhaust stroke? Why we are not representing the generally in any book, if you see the Otto cycle, it will start from 1, 2, 3, 4, 1. That's all. It is not going to represent if the 5, 6 or 6, 1. That is what it is representing, the intake stroke and the exhaust stroke. Because in the Otto cycle, we assume that intake stroke and the exhaust stroke is taking place at the atmospheric pressure. Okay, intake stroke and the exhaust stroke is taking place at the atmospheric pressure. So it will be only a line will come out. And it has a opposite direction, so it will be going to the cancel out. In reality, intake stroke and the exhaust stroke in the gasoline engine is not takes place at the constant volume, constant pressure. Constant pressure, that is the atmospheric pressure. I'm talking about the natural aspirated engine. So, so that's one more very deviation from the realistic conditions. Anyone can tell me that in actual gasoline engine, the intake strokes is occur at what temperature? It is less than atmospheric pressure or at atmospheric pressure or above the atmospheric pressure?
Less than atmospheric pressure.
Less than the atmospheric pressure. And the exhaust stroke?
Greater than atmospheric pressure.
Greater than atmospheric pressure. That's really very good. Then it means what we are seeing here, line only a line 5, 6 or 6, 1. Since it is occurring at a constant pressure, then it is that is atmospheric pressure. It is representing by a line only. But in reality, the intake stroke takes place less than the at less than the atmospheric pressure, where the exhaust takes place slightly above than the atmospheric pressure. So that there will be no line here. Instead of that, there will be a small loop will be created here. That loop, do you think it is good or bad? Good or bad in terms of, do you think that loop, it is a positive work done or it is a negative work done? Because if there is a loop, then the area will give you the work done. The work done that what we are going to get because of the pressure and intake and exhaust stroke is taking place at different pressure. So whatever the work, the area of that loop will come, is it going to be the positive work done or it is a negative work done?
Negative.
Negative work done. And that loop is called pumping loss. Pumping, pumping loss. And that is the negative work done. Think about that. And that negative work done, it is particularly in the gasoline engine. It is a very high, particularly when your engine is running at low speed and low load condition. If somehow, and that is still right now with your all the production engine, that pumping loss is significant at the low speed and low load condition. We'll discuss a little bit more about that. And that is one of the gray area, that how we can convert this negative work done or part of the negative work done into the positive work done. And that will give you a really very good jump in the thermal efficiency of the gasoline engine. So these are some of the areas that still needs to be explored in order to improve the performance of the gasoline engine. And that is, we'll discuss about that. Okay. So it is almost now time is over. Thank you, all of you. And still with my best efforts, not all of you are participating in the class. And my humble request to all of you, please don't give me the excuse that our mic is not working. Okay. Please do something. Okay, let us have a workable mic so that we can communicate with each other. And if I'm calling someone and if you are not responding, it is also giving a very, very bad impression, very bad impression. And I'm calling 2-3 names, and if you are not responding, obviously I know that the name of the student. Okay, so respond it back, have a workable mic. Okay, and then that's all. That is what the minimum expectations from you. Okay, so I'm stopping here. See you in the next class.